So here we're going to talk about how activation parameters can help us understand the mechanism of a substitution reaction. So activation parameters refer to quantities like thermodynamic quantities related to making the transition state. So for example, we've talked about the activation energy, which we sometimes call delta G of activation, and we give the little sign, the double dagger, to indicate that it relates to the transition state. And so here we can break that delta G into the delta H and the delta S components. And that will give us this equation, which is called the Eyring equation. And so basically, the Eyring equation is kind of like the Arrhenius equation in that it tells us about the relationship between temperature and rate. But if we sort of, break this, so this could be we can imagine making this a line where this is the slope, and then this whole thing is the y-intercept. And from, if we measure the rate as a function of temperature, we can pull out the entropy of activation from the slope of the line. Okay, so entropy of activation, we're going to think about how the ordering of the molecule changes as we make the transition state. So if delta S double dagger is negative, then that means that the transition state is more ordered than the starting materials. So that would be consistent with an associative mechanism because we imagine that we have two particles that are our starting materials that become one particle, the intermediate. So we start with our complex and we add our incoming ligand to make our 7-coordinate intermediate. And so making that transition state, as those things are coming together, we have two independent particles that become one. So entropy decreases. Our delta S of activation is negative. On the other hand, if our delta S of activation is positive, then that supports a dissociative mechanism, because in that case, we have one particle, the overall complex, that is becoming two particles, where we have the dissociation of the ligand. Okay, so that would mean that as we make the transition state, we are increasing entropy because we had one particle and it's splitting into two things. We can also measure the volume of activation by seeing how the rate of the reaction changes as we change the pressure. So these experiments can be a little bit hard to do physically, like we're not going to do them, but one could. And so we see here that there is a volume of activation, and it is proportional to RT, so R is the ideal gas constant, and the temperature, and the partial derivative of natural log of the rate constant with respect to the pressure at constant temperature. You don't need to be able to use this equation, where it just helps us to understand that there is a volume of activation that is dependent on the rate. And once again, the sign is what will help us work out the mechanism, or at least support a mechanism. If the volume of activation is negative, then that is going to support an associative mechanism, because two things became one thing. So if we imagined like the volume of the starting materials, so we have our starting complex and our incoming ligand, and if we sort of draw an imaginary line around them, okay, and then when we make the transition state, they'll come together to make that 7-coordinate intermediate, and the imaginary line has gotten smaller. So if delta V double dagger is negative, then the volume of the starting materials and the transition state has decreased. Okay, so the volume has gotten smaller. On the other hand, if delta V of activation is positive, that supports a dissociative mechanism because one thing is becoming two things. If we do the same exercise and we imagine that our initial complex, we can draw an imaginary line around it, is dissociating to form two independent things, then our imaginary volume has gotten bigger. So delta V is positive. So these activation parameters help us think about quantities that we can make measurements about and use those to support one mechanism or the other. Once again, for interchange, we don't have specific rules. Instead, interchange associative mechanisms will be more like the associative, and interchange dissociative will be more like dissociative